Hi class, today we'll be talking about another subspace that is connected to a matrix A. In this case, it will be the null space of A. So the first one was the column space, now the null space. Column space sort of intuitively makes sense even from the label, from the name. It is the space of the columns of A. Now here also the null space makes sense. The word null indicates a zero, and then, well, a space is a space. So in some sense, the null space is a space of zeros, if you wish. Let's look at the formal definition. The null space of A consists of all vectors x which solve ax equals 0. So the null and that zero or this zero is where null comes from. But so you have to think that the x's which solve this equation ax equals 0 are what constitutes the null space. If a matrix A is m by n, so if it has m rows and n columns, then the vectors are in Rn. I will show you why this is the case. You don't have to memorize which is, whether the column space is a subspace of Rm or an Rn. You should just understand the size of the vectors that come into play. So just from matrix multiplication, it makes sense that this vector has n components if the matrix is m by n. Now, let's check that the null space of a matrix A is really a subspace. Yesterday we defined what subspaces are, and the most basic way to remember that is if we have a vector in the null space, or if we have two vectors in the null, if we have two vectors in a subspace, then all of their linear combinations also need to be in the subspace. If we can verify that, then whatever set we are claiming to be a subspace truly is a subspace. So we want to take two vectors that are in the null space of A. So let's say take vectors x and y in the null space of A. What we want to do is we want to show that cx plus dy is also in the null space of A, where c and d are some scalars. Now the first thing we have to understand is, what does it mean for these vectors x and y to be in the null space of A? We have to always remember the definition of the null space, which says that the null space consists of vectors x which solve ax equals 0. Now, of course, x is just a name. If x and y are in the null space of A, what that means is that ax is 0 and ay is 0. So both x and y represent solutions to the equation ax equals 0. All right, so we know that ax equals 0 and we know that ay equals 0. How do we use that to show that cx plus dy equals 0? Well, let's just try, that a times cx plus dy equals 0. So to show that cx plus dy is in the null space of A, we look at a times cx plus dy. Now, just using standard matrix multiplication, we have that this is a times cx plus a times dy. Now, these constants c and d, they can come out here. They can change places. You could first multiply a by x and then multiply everything by a constant, or you could first multiply x by a constant and then multiply a times x. These are allowed operations with matrix and vector multiplication. So here we truly have C times AX plus D times AY. Now AX is 0 and AY is 0. C times 0 and D times 0. We have C times the 0 vector plus D times the 0 vector. Together they give us the 0 vector. So this means that Cx plus dy is in the null space of A, or rather NA truly is a subspace of Rn. All right, now let's look at an example of how to find the null space of a matrix. So here's a matrix, very small, nothing complicated about it. We have the second row being 3 times the first row. So we are looking at the null space by looking at this equation, AX equals 0, and trying to solve it. So you actually had this on the first test. When you look at the equation AX equals 0, sometimes it's solvable directly when you look at the matrix A. But what you could also do, now in this case, look at this. If you think of 0 as a vector B could be 0. Our standard way of approaching this is you have your matrix, you could augment it like this, A0. You carry out elimination, and you get to the equivalent system with the matrix U and 0. So AX equals 0 takes us to UX equals 0. So we actually don't really have to keep track of the zeros on the right-hand side because we know that the zeros after elimination will continue to be zeros. And whereas when we had AX equals B, that changed into UX equals C. But when B is 0, C is also 0. So the strategy will always be to carry out elimination because whatever X solves AX equals 0 is the same X that solves UX equals 0. So actually, the null space of A is the same as the null space of U. I'll put that comment here. The null space of A is the same, is truly equal as the null space of U, where U is that reduced upper triangular matrix that we get from A. Now, let's do this for the matrix that we have over here. So we have 1, 2, 3, 6. That one elimination step is R2 minus 3R1 into R2, and we get 1, 2, 0, 0. So what we're looking for now is sort of combinations that are going to give us combinations of the columns that are going to give us 0. The combinations of the columns of U that give us 0 are the same combinations that give us 0 when we combine the columns of A, even though the columns of U and the columns of A are not the same. Absolutely not. Now, one way to look at it is that when you look at the matrix U, you have a pivot column. So this column is a pivot column. And the column that doesn't have a pivot is what's called a free column. So you can think of the first column as coefficients for the first component of X, which is X1, and the second column for the second, coefficients for the second component. If we were to write out the system, right, we have something like X1 plus 2X2 equals 0, and the second equation just gives us 0 equals 0. Which is not a contradiction. It's something that makes sense, but it doesn't really give us any information to find X1 and X2. So we can find a special solution that solves this equation that is in the null space of A. And the way you find that solution is by setting up x2, which is the variable of that free column, to be equal to 1. So if we set x2 to equal 1, then let's find x1. Then we have x1 plus 2x2 equals 0 gives that x1 must equal -2. Now let's check. So we are claiming here that x is -2, 1. Now, does this x solve ax equals 0? And does it solve ux equals 0? Well, when you do row by column multiplication, you see, yeah, this definitely solves ux equals 0. If you have 1 times -2, so 1 times -2 plus 2 times 1 is definitely 0. When you apply this row times x, you get 0. When you apply this row, well, it's 3 times the first row, so you're going to get 0 again because you have 3 times -2 is -6, plus 6 times 1 is 6. You get 0 again. Now, we are not done. This vector x is just one special solution to the equation ax equals 0. Why is it special? Because we set the variable that corresponds to the free column to equal 1. So this is just one special solution. But you see, it describes everything. So the null space of A, yesterday we talked about span of a set. The null space of A is completely described by this one vector by saying that the null space of A is the span of this vector x, or the special solution, with components -2, 1. So what this says is that all linear combinations of this x, which literally means all multiples of this x, will do the trick. In particular, certainly 0, 0 will do the trick. But 0, 0 is always going to be a solution to ax equals 0. Question is there more? Now, let's look at one more example. So let's look at another matrix A. I don't want us getting confused with different letters. Let's take the matrix A to be 1, 2, 2, 4, 3, 8, 6, 16. The very fact that we have 4 columns with 2 components tells us that definitely we're going to have linearly dependent columns. So let's carry out that elimination step that is going to just eliminating under the pivot to give us that upper triangular matrix U. So the operation is R2 minus 3R1 into R2. And we are getting 1, 2, 2, 4, 0, 2, then 0, and 4. Okay, so we got to our upper triangular form. So this would be our U. We have one pivot and another pivot. I know it doesn't really look like an upper triangular matrix, but what we sort of call an U matrix, or this is in the case of rectangular matrices called row echelon form of the system. And what the only requirement for it is that below and left of all the pivots, we have zeros. That's what defines the row echelon form. So just keep on eliminating under the pivots. You get wherever you get, you have a row echelon form. Now, as I said, if we have, I should write here, AX is 0 is what we're looking at on the left. And here we have UX equals 0. The same X's do the trick. Now, these two columns are the pivot columns, whereas these two columns are free now. The variables associated with them are x1, x2, x3, x4. Remember, these are the components of X, and this is a good example to see why, say, the null space in this case would be a subspace of R4, because there are 4 columns in the matrix A or in the matrix U. So when you look at a particular matrix, you know immediately where the null space needs to be. The null space would be a subspace of R, n, where n stands for how many columns the matrix has. All right, so how are we going to find the special solutions to this case? So we want to find the special solutions. So how to find the special solutions to the equation. So what we're going to do, because we have 2 free columns, that means we're going to have 2 special solutions. So whenever you have a pivot column, that gives you sort of uniqueness in some sense. Free columns give you special solutions that are going to go into the null space. So what you do is you set one free column to 1, all others to 0. Now in this case you only have 2, so you do this one at a time. So let's say we're going to set x3 to equal 1 and x4 to equal 0. Now we can use back substitution to find what x1 and x2 must be. We'll look at the second equation. The second equation says 2x2 plus 4x4 equals 0. Here x4 is 0, therefore x2 must also be 0. Now we look at the first equation, which says x1 plus 2x2 plus 2x3 plus 4x4 is 0. Now what do we know? We know that x3 is 1, x4 is 0, x2 is 0, and so we can find x1 easily. x1 is equal to -2. So the first vector that we have is x equal to -2, so that's x1, 0 for x2, 1 for x3, and 0 for x4. Before we continue, let's confirm that this truly works. So we want, let's look at the second row. This row, dot product with this column vector, what do we get? Well, it is obviously that these two, their dot product gives us 0, because wherever we have non-zero here, we have a 0 there, and vice versa. So 0 times -2 is 0, 2 times 0 is 0, 0 times 1 is 0, 4 times 0 is 0. So that works. Now, what about the second special solution? So the second special solution, for the second special solution, we're going to set x3 to be 0, x4 to be 1. Again, we start with the second equation. We're getting 2x2 plus 4x4 is 0. Now x4 is 1, so what we have here is 2x2 plus 4 is 0, therefore x2, That was not good. Therefore, x2 equals a negative 2. Now let's go to the first equation in u, which is x1 plus 2x2 plus 2x3 plus 4x4 equals 0. We know that x4 is 1, x3 we've set to 0, x2 is a negative 2, and x1 is what we're trying to find. So what do we have here? So from x2 we have a negative 4, from x4 we have a 4. It turns out that x1 must be 0. So the vector x in question is going to be, this is another x vector, so x1 is 0, x2 is a negative 2, x3 is 0, x4 is 1. If you take the dot product here, this row times this column, really what matters is the values here and here. You have 2 times negative 2 is a negative 4, plus 4 times 1 is 4, therefore you get a 0. And then here you have 2 times negative 2, which is negative 4, plus 4 times 1 is 4, you get 0 again. So we see that, whoops, that doesn't look great. Okay, I'll fix it for the notes to submit in class. Or I guess I could do it right now. So you see, we find these special solutions, and they now allow us to describe the null space completely. The null space of A, which is the same as the null space of U, is the span, which means all linear combinations of the set of these two special solutions, negative 2, 0, 1, 0, and 0, negative 2, 0, 1. So what this says is that I could take literally any linear combination of these two vectors and check that they solve ax equals 0. Let's do just that. So let's say let me call this y. Y equal to 3 times negative 2, 0, 1, 0 plus 2 times 0, negative 2, 0, 1. What we are getting is negative 6, negative 4, 3, 2. So this vector is not that obvious to see that is that gives us a solution to ax equals 0, but let's just check. So if we do, let's check with the second row of u. So this row dot product with that row, do we get a 0? 2 times negative 4 is negative 8, plus 4 times 2 is 8, we get 0. And you see, the same is also true with the first row. You can take your time to do that small calculation. But the point is that when we take something from the null space, or when we take a linear combination of these two vectors, we know that the result is going to be a solution to ax equals 0. Now, that doesn't give us much new because it's already a linear combination of what the vectors of the special solutions. So for us, once we find the special solutions, we will know that we are actually done. So just to complete my thought here, when I take this y, then we know that ay is 0. Why do we know that ay is 0? Because we took that y to be a linear combination of the vectors that describe the null space of A. Okay, in the next video, we're going to be talking about the reduced row echelon form of a matrix.